Welcome back. Yes, so I promised you to explain why this is true. So here's the statement. You take the times p map on the circle group. X goes to p times x. P is greater or equal to. It's an integer. Think of 10, think of 3, whatever. Then we can look at the space of invariant probability measures. We have done that the last 2 lectures a bit. And that's a convex weak star compact set by itself. And as often, somehow the extreme points of this convex compact subset are interesting. They are most interesting somehow. And the extreme points are the ergodic measures. That's what we already understand. And now something weird happens in this particular example of this particular dynamical system. For other dynamical systems, maybe this is not as weird, but for this one, it's quite weird. Namely, the extreme points, the ergodic measures, are dense in the space, in this convex set that we are looking at. In the weak star topology. That's the one that is relevant for us. Yeah. So let me try to explain this, why this is true. I sold it a little bit. I could say more, but by saying more, it sounds a bit less impressive. So I said a bit less. Namely, the ergodic measures that are dense are actually periodic orbit measures. So I will construct to you for a given, not necessarily ergodic measure, I will construct to you a periodic point for which the periodic orbit measure, which is just the average over all the points in the periodic orbit, is close to the measure that you gave me. There are lots of other ergodic measures around, but I don't need them. I can already prove that statement using just periodic orbits. Let mu be your favorite TP invariant measure. Don't think ergodic because otherwise there's nothing to prove. We can still say we can approximate an ergodic one also by periodic ones. But I'm not assuming ergodicity. By Grein-Millman, I'll remind you what it says by making the statement here. That was one of the black boxes that I explained from functional analysis yesterday. By Grein-Millman, we can approximate mu arbitrarily well in the weak star topology by a finite convex combination of ergodic measures. Let me make it even more clear what this statement means. For any finite list F1 up to F k of continuous functions on the torus and any epsilon greater than 0, there exists ergodic measures mu 1 up to mu L ergodic TP invariant probability measures, and the coefficients for the convex combination, and C j greater equals 0 with the C1 plus CL equals 1. So let's even say Cj greater equals 0 if one guy doesn't show up because its coefficient is 0, then why did you write it in the list? Just drop it. Such that. So that's now the weak star approximation statement. You haven't seen it much because it didn't, yeah. I just told you that it exists and I talked a little bit about it, but you'll have or will see it in functional analysis. Such that when I integrate one of my finitely many test functions, fi, against my original measure that I started with, and I compare this to the integral with respect to the convex combination. Let me write it like this. When I make this comparison, how does my original measure integrate fi, and how does the convex combination integrate fi? I see it's basically the same. It's I only have an error of epsilon. And I have this for all test functions, for all these finitely many test functions simultaneously. Because these test functions and the epsilon, they define the neighborhood of my measure in the weak star topology. And then Grein-Millman is saying there is a way to find a convex combination, a finite convex combination of the extremal points that is in this neighborhood. And that is precisely that statement. So in words, this part is the same thing as this, a little bit more formally. Okay? Now the mu i's, no, mu j's I call them, the mu j's are ergodic. So I can apply the ergodic theorem and I get the strongest possible statement for the ergodic theorem, namely that for almost every point, for the mu j, almost every point, the ergodic averages will converge to the right expression. The right expression is the integral of fi d mu j. Right, so applying the ergodic theorem pointwise to fi and mu j, we see that for mu j almost every x in the torus, we have, when I average, I didn't use n yet, very good. When I sum, I and j already used, that's bad. P is also not good. A equals 0 to n minus 1. F I Tp to the A of my point x, so that's the ergodic average of my point x under my dynamical system for my function fi. Then this converges as n goes to infinity to integral fi d mu j, right? That's what I know. That's the ergodic theorem. So I can take one such point. I only need one generic point, so I take one. Let's say xj is generic for mu j. Sorry, didn't define generic yet. I need one point that satisfies this, and I call it xj, because it's a good point for mu j. Let xj in T be a point satisfying this for all the functions that I care about, so for I equals 1 up to k. Right? Almost every satisfies it for F1, almost every satisfies for F2, so almost every satisfies for F1 up to Fk. And I take one guy that does that. Okay? Of course, that point is not periodic, so I can't just say, can't just declare victory. So I need to create a periodic point. And besides, it's not one at the same point. I want one point that approximates mu, right? So what do? I take a capital N, which is a large number, so that this convergence here is also already working somehow. Let capital N be large. Well, later, it's meant to be a sketch, right? It's not. Let capital N be large, and let the base P and let A j comma 1, aj comma 2, and so on. Those are numbers from 0 up to p minus 1, be the base P digits, the expansion of xj, right? I can think p is equal to 10, and then I just write my xj in decimal expansion and get some numbers between 0 and 9. And it's the same for p equals whatever. And I get numbers, I get these digits that depend, of course, on the position that I use them in, and I also depend on the xj that I'm using. And now I define the periodic point. We define x to be the rational number whose base P expansion equals, I start with trying to approximate what x1 is doing. x1 is my good point for the first measure. So I use the digits that x1 is doing, and I use them a lot. So I go with a11, a12, basically up to an, but not really up to an, because I also want to build in the coefficients in the convex combination up there. So I go up to integer part of C1 capital N. Right? I can do that. Those are digits. I can use any digits I want to define a number. And now I switch over to the second good point for the second measure. And start again in the beginning. A2, 1, A2, 2, and so on, up to A2, fractional part C2 capital N. Then I start with the digits of the third good point, and so on, and so on, and so on. And at the very end, just to make the dots finish, I start with how many measures do I have? L measures. So I the last block is AL, 1 up to AL, fractional integer part CL, capital N. And this is just a finite thing, but I want a periodic thing, so I just repeat this periodically. So that's now a real number defined by a periodic base P expansion, and that, of course, is a rational number. And it's also a periodic point for the measure, for the transformation TP, because after I shift basically capital N times, it will close up. It's not precisely capital N times because the Ci don't divide, yeah, whatever. You see what I mean. Okay. The claim is now that that when my x is equal to that, and I sum up the Dirac measures over the whole orbit and divide by the length, I get an ergodic measure because it's one periodic orbit. A periodic orbit, and this counting measure on the periodic orbit is always an ergodic measure. No questions asked. Because to be invariant, you have to have the whole orbit in the set or the whole orbit outside the set. Because it's only one orbit. Then X is periodic with period close to, well, no, yeah, it's really close to, it's sort of just a bounded mistake, close to capital N, and we define mu as the normalized counting measure on the orbit. This is definitely going to be a useful thing for us, so let's give it a name. And here we have another nice property that also deserves a name. And what we want, yeah, sorry, of course that's not mu. That's mu tilde. Mu is the thing that we started with, right? Mu is the thing we started with, then we got the mu j's and the convex combination. And now I defined an ergodic measure. And the claim is that the ergodic measure I can put in the, instead of this convex combination, I could put here this mu tilde and still have something like that. Yeah, okay, if it's 2 epsilon or epsilon, I'm not bothered. Okay, I'm not writing down the glorious triangle inequality that does it, but I want to explain what's happening. Probably already see what's happening. So note that mu tilde is ergodic. I said that before. Let's also have a record of it. And as F1 is continuous, most, and so uniformly, of course, most points in the orbit of X in the first, no, I should make this a bit more precise. No, I don't mean the whole orbit. I mean only the stretch of the orbit up to C1n. Most points in the orbit up to TP C1 capital N X are very close to my xj that I built and satisfies the diamond up there, right? If I look at the very beginning of my x and write here, starting from here, nothing, just zeros, then I define a rational number that's very close to x1, right? Because lots of digits agree with what the digits of x1 are. And that's also true if I apply TP once, because all I'm shifting, I'm losing that digit, and the difference sort of gets a bit closer, but it's still far away. So the problem happens sort of at the end. If I look at the last 5 points in the orbit, then I have only 5 digits that are the same in my x and in my xj. And that might not be good enough for the function f, which is uniformly continuous, hence has some epsilon delta stuff. But I think of capital N as super large, so these 5 places where the digits are now quite quickly different are irrelevant. When I average over all the digits, or all the orbit from the original point up to this future point. Close to xj/r, respectively its orbit, points. Yeah, so that's part of the explanation. If f1 is continuous, most points of this orbit are very close to xj and its orbit. We obtain that when I average over this first piece, C1 capital N, sum of, what's the index I always use? A equals 0 to n minus, what's the n? It's capital C1 capital N minus 1. That's how far I average. And then I compare my test function fi at the future point, at the orbit point of x, and I make the comparison to what my x and my xj is doing. And I could even put the absolute value inside, and I will know that this is less than epsilon. For large capital N. Yes?
Isn't this only true for like above in the second zero that's close to xj should be x1?
So x is close to xj, tpx is close to tpxj, and so on. That's what I mean. I don't go beyond the C1 capital N. I only go up to C1 capital N. And I'm shifting both. Maybe I have written it down incorrectly or not, a bit confusingly, but I'm really shifting my x and I'm shifting my xj. And they have the same digits up to C1 capital N. And when I get close with the A to the C1 capital N, then the difference between those 2 points could be bigger than the delta that is needed to get the uniform continuity kick in. That could happen. But how often does it happen when I think of capital N being super large? It can only happen fixed amount of time depending on delta. And if capital N is super large, I can still beat it by saying those finitely many points, boundedly many points in a growing piece of an orbit will not matter for my average. But thank you for the question. I do this for all, not just for the, I did this for the first guy originally. But of course I do this for all the guys.
Yeah, that was my question.
That was your question. Then it deserves a chocolate. Yes, no, it deserves a chocolate. Thank you. Yes. It's just for the, I stated it for the first guy. And afterwards, I use the second guy and get a similar estimate. And then I use the third point, similar estimate. But I'm actually averaging over all of them. So how big is the first portion compared to all of them? Well, basically C1, right? The integer part is plus minus 1. Who cares when capital N grows? So by putting it all together and by also using this here, I get as a conclusion, and I only write down the conclusion, a free epsilon statement, which I'm happy with, for large capital N. Applying the same argument for j equals 2 up to how many measures to have L again, we obtain in total an estimate of the form I integrate Fi with respect to my original measure mu. I integrate my Fi with respect to my periodic orbit measure that I defined. Maybe it's a periodic orbit measure that also depends on the capital N that I've chosen. And this will be less than 7 epsilon for I equals 1 up to k. And that is the statement that we wanted. Maybe an easier statement would have been, I can, if I have a combination of two ergodic measures, and I just take the midpoint between them, 1/2 the first ergodic measure plus 1/2 the second ergodic measure, I can apply this construction and it would very easily give me a sequence of periodic orbits that for the first half of the period behaves like a point, like an almost everywhere point for the first measure, and then just says, no, I don't like that measure, and behaves for the second half of the period like a good point for the second ergodic measure. But by concatenating these two behaviors into one period, which I can, because what is the restriction on digits in the base P expansion? None. By doing this concatenation, I obtain one periodic orbit that will converge in the weak star topology when I let the period grow to a non-ergodic measure, because it will create in the limit precisely the midpoint between the two ergodic measures that I started with. And all I'm saying is this construction is so flexible I can actually approximate all invariant measures, because all invariant measures can be approximated by convex combinations of ergodic ones, and then the method works. And of course, I did this for times P on the shift map, but secretly I used the full shift, right? So for the full shift, it's the same behavior. Good? Any questions? I didn't want to underestimate the complexity of the argument by saying free, I mean. And it's definitely not an epsilon because there are quite a few. No, that I don't want to do. Yeah, 17, they are just meant as a joke. Good. I said generic. Maybe I should tell you what it is. Definition. Let X be compact. T from X to X continuous. Mu an invariant measure. Typically ergodic. I don't need to write it as an assumption in a definition. Then X in X is called generic for T and mu. Maybe they are sort of God-given, and then I don't need to mention the transformation and the measure. But if they are not sort of completely obvious, then I would mention them. It's called generic if the ergodic theorem holds for all functions. That's a bit much. How could it hold for all functions? Well, let's settle on a little bit of a restriction for all continuous functions. If 1 over n, sum from j equals 0 to n minus 1, f of t to the j x converges to integral f d mu as capital N goes to infinity. Proposition, it's a nice statement. Let mu be in addition ergodic, then mu almost every x is generic. It's just the ergodic theorem, right? There's a change in the order of quantifiers. Yes, you have a question? If for all, I said it, yes, for all f in C of x. Thank you. Yes, but it's an important point because what I want to do is I want to just apply the pointwise ergodic theorem. Because the pointwise ergodic theorem does say that, right? It does say this in a different order of quantifiers. What I want is I want a point that works for all function. The ergodic theorem says for every function, almost every point will be good. So if I only have countably many functions, I'm in business. How big is the space of continuous functions on a nice space, X compact metric? Always continuum, right? So it's of course not a simple, trivial consequence of the pointwise ergodic theorem. It's just an easy consequence of the pointwise ergodic theorem. So we'll prove it. And yeah, the proof will also show why you shouldn't expect something like that, where you take all, say, bounded measurable functions. That would not be a simple consequence. I think that's completely wrong. It's just nonsense. Because you can always screw up a measurable function on an orbit, right? So if someone claims this point will have perfect behavior for all measurable continuous functions. I'll take the characteristic function of the orbit, and I probably get something that's not correct, right? So I can't do this with continuous functions because characteristic function of the orbit won't be continuous. Maybe the orbit is dense, so if I'm 1 on the orbit, I'd need to be 1 everywhere. And then it's again correct, the statement that I want. What am I going to say in the beginning of the proof? What's the first line? What would be very helpful here now, after I've talked about, oh, countable is fine and so on. Yes?
Maybe the separability?
Yes, precisely. You want the chocolate? Yes, good. So if X is compact metric, C of X is a separable space. So we can find a dense countable subset with respect to the soup norm. And then apply the pointwise ergodic theorem to all the things in the dense countable thing, and then do an approximation argument and say the point that is good for the dense countable set is actually good for all functions. Okay. Let D in C of X be dense with respect to soup norm and countable, which exists maybe, if you want, as a consequence of Stone-Weierstrass, but yeah. By the pointwise ergodic theorem applied to all F in D, we have one over n sum j equals 0 to n minus 1 f of tj x converges to integral f d mu for as n goes to infinity for mu almost every x and all f in this dense countable set. We claim that these points are generic. So it is enough to know the convergence on a dense countable subset, and then you get the convergence for all continuous functions. Yeah, and let's say everything is real valued. We don't need complexes right now. So we can talk about inequalities and prove the statement about inequalities. If you have proven the statement for real valued functions, you have proven the statement also for complex valued functions. It's quite often like that in this context. Yeah. So is there a question? No. Let F0 be arbitrary, not in the dense subset. Let epsilon be greater than 0. And let x be a point as above. Meaning this x satisfies the ergodic theorem for all f in D. We want to show it also satisfies the ergodic theorem for F0. Then I'm studying this average F0, t to the j, x. I'm studying this average, and it's a real valued thing, so I can look at the lim sup, lim inf. Let's look at the lim sup, and the statement will be easy. Degeneralized to the lim inf. For n goes to infinity. And what do I know? I know that my D is dense, so up to an epsilon I can find an F in D that is very close to F0. There exists F in D with F minus F0 subnorm less than epsilon. And so now I look at this expression. I say, this F0 of t to the j minus x is actually less or equal than the f of t to the j x plus epsilon, because my subnorm is less than epsilon. Subnorm of the difference is less than epsilon. So I can switch over from F0 to F. And the lim sup is then estimated from above using the function f instead. At the cost of an epsilon. What do I care? But for f, I don't need to look at lim sup. I can look at lim because f and x, they work together well. And the limit in that case is precisely the integral of f d mu. F is my function from the dense subset plus epsilon. But that's not what I'm interested in. I'm interested in comparing it to the integral of f0. So I'll say again this f is less or equal than f0 plus epsilon, again because of the subnorm. So this is less or equal than integral f0 d mu plus 2 epsilon. And then I look at the very beginning and the very end. And I notice that there's nothing at the very beginning that depends on epsilon, and nothing at the very end that depends on epsilon, except the very epsilon that appears here. So having this inequality, I can let epsilon go to 0, and I get that the lim sup of the average of f0 is bounded by the integral. Same applies to the lim inf, so I get the statement. This gives limit 1 over n, sum j equals 0 to the n minus 1, f0 t to the j x is equal to integral f0 d mu. It's sort of a natural concept. We also say that the orbit is equidistributing. When you have a point that is generic, you have an orbit, and you have a desired distribution in the space, which is your measure mu. And instead of saying the point is generic, people also say the orbit is equidistributing and mean the same thing. Good. I think I'll take the break here. We'll continue after the break with the notion of unique ergodicity. Good. Welcome back. We had some discussion in the middle of the break concerning the first line here. So how does this work? I'll only tell you quickly, not writing down anything because I think it's rather functional analysis or analysis. It's actually a quick corollary of Stone-Weierstrass theorem. First of all, you need to know that x is separable. And maybe for that, we should point out that everything is metric that I'm talking about, right? So mu ergodic and x metric, otherwise I'm not talking about it. And if x is metric, then you just take 1 over n, you cover x by 1 over n balls. Finally, many are sufficient, so you get finally many 1 over n dense points. Where you vary n, you get countable points that are actually dense. So that's the separability of x. Now I take the distances to any of these points and define this way countably many functions. On x, I'm not claiming that they're dense, but if I now take the Q algebra generated by these distance functions and the constant function 1, then you can hit it with Stone-Weierstrass and it satisfies all the properties, and hence this thing will always be dense. And that's countable because I looked at a Q algebra generated by countably many functions. So that's clearing up this thing. And of course, this countability was important so that I can take a countable intersection of full measure sets and I get a full measure set. Good. And as promised, now we want to talk about the notion of unique ergodicity. It's a very nice thing concerning generic points and also concerning this convex set of t-invariant measures. So definition, xt is called uniquely ergodic if there exists only one t-invariant and ergodic probability measure, a t-invariant probability measure on X. Obviously Borel. Theorem. The following are equivalent. Of course, under the usual assumptions, I'm not writing it down. X is compact metric. T is continuous. 1. Xt is uniquely ergodic. Two, there exists precisely one only one t-invariant and ergodic probability measure. I misspoke up there. I didn't want to put ergodicity into the definition, but I could have, because it gives me an equivalent notion. 3, I want to say every point is generic, but I want to say every point is generic without mentioning the measure, which is a bit weird, but I don't want to mention the measure because I want to give an independent condition somehow. For any f in C of x, there exists a constant, secretly the integral of the function with respect to the measure in 1 and 2. This is a constant Cf, so that 1 over n, sum j equals 0 to n minus 1, f of tilde j x converges to Cf as n goes to infinity for every x in x. 4. Same as in free, but with uniform convergence. All equivalent. Proof. 1 implies 2. If there's only one t-invariant measure, then it better be ergodic because we proved there's always an ergodic measure around. So 1 implies 2 is obvious. It's easy, it's check. 2 implies 1 relies again on the same thing that we have used a couple of times, Klein-Millmann. Klein-Millmann is saying any measure can be approximated by a finite convex combination of ergodic measures. But how does this work if there's only one ergodic measure? Then any convex combination of this one ergodic measure used several times is just this one ergodic measure. And when you take the closure of this one ergodic measure, you get this one ergodic measure back. So follows from Krein-Milman. Okay. So how about condition free? One implies free, maybe. I mean, 1 and 2 equivalent, we know that now, so we could also use that it's ergodic. It doesn't matter. We can go from 1 to 3. We know that there's only one invariant measure mu. That's what we're assuming in 1. And we know it's ergodic, as explained before. Let mu in mxt be the unique t-invariant probability measure. Let f be in C of x and x in x. Then any weak star limit of 1 over n sum j equals 0 to n minus 1 t j delta x is t-invariant. We said that. We have proven that last week. That was our starting point to show that invariant measures actually exist. And we could put here any measure that we want. Any measure whatsoever that we want, we could put here. And when we do this averaging and take any limit whatsoever, it will always be an invariant measure. Okay? Is T invariant? That's the statement. But for us, however, for us, under the above assumptions, this means that mu is the only limit of any converging subsequence. It doesn't matter which subsequence you pick. If it gives you a converging expression here, the limit will be mu. This sounds a bit weird. Sounds like a very complicated statement. How does this compare to, it actually converges to mu? Someone said it's the same. Who said that? Did someone say it's the same? No, I thought I heard it's the same. It is the same. But is it obvious, tautologically true, or does it need a little bit of information to make that statement? Yes?
You need the sequence to be a Cauchy sequence?
No, a Cauchy sequence converges. So then there's nothing to talk about. If we assume that it's Cauchy sequence, it just converges. So we have a topological space. And in this topological space, we have a sequence, let's call it yn. And what we currently know is that for any subsequence of yn, the limit is y. It's the same y, the same limit. I'm claiming when this happens that no matter which subsequence you picked, you always get the same limit. This can only mean that the whole sequence already converged. You had...
I'm not sure if you want to know this, but there's a point.
Yes, that's a criterion. But does it help us? I mean, the criterion, I need to repeat it for the recording. The question, the possible hint was, convergence is equivalent to any subsequence has a subsequence that converges to that point. That is helpful. That is helpful.
I mean, the space is compact.
Precisely. MX is compact. So in a compact space, this is an actual criterion. So because MXT is compact, we can now make the jump to the statement that this actually converges. It's the second one, right? Then make it fair. Good. So how to do it formally? You say, if that thing would not converge to mu, what does that mean? Then there is a neighborhood that infinitely many times is not visited by that. That's a subsequence. And that subsequence has a subsequence that converges because we're in a compact space. And then we get a contradiction because of the subsequence that's outside the neighborhood, we can find a subsequence that converges to the point, to the measure mu. So that gives you a contradiction. This implies that 1 over n sum j equals 0 to n minus 1 t j star delta x converges to mu, because if it doesn't, then there exists a neighborhood n of mu and a subsequence staying outside of n. As m of x is compact, m of x super t is compact, this subsequence would have a subsequence converging and converging to mu, because we said mu is the only possible limit. This is the end of this long part of the second part of the sentence. So I obtain that this actually is happening. But what does that mean? Convergence is happening in the weak star topology. So when I evaluate this at a continuous function, it actually means precisely what I want it to mean, namely that the ergodic averages converges to CF, which is the integral of f with respect to mu. This means that integral f d 1 over n sum j equals 0 to n minus 1 dj star delta x converges to integral f d mu, but that complicated expression is the same thing as 1 over n sum from j equals 0 to n minus 1 f of t to the jx, and this I'll define as CF, and this is true now for all continuous functions and as n goes to infinity. So that is 1 implies 3. And in particular, I know what the constant is. The constant is really the integral of f with respect to mu. And now, maybe I show 3 implies 2. Two is that there is only one ergodic measure. Don't think it's particularly important. You can also go directly to 1. 3 implies 2. Suppose mu1 and mu2 are both T-invariant and ergodic. Let x1, let xj be generic for mu j for j equals 1 and 2. So I have 2 points in my space, and the first one is generic for the first measure, the second one is generic for the second measure. They exist, right, because that was what we have shown before. Then, by definition of genericity, we have, when we take a continuous function and do the ergodic average, the sum goes from k equals 0 to n minus 1, tk xj. That converges now to integral f d mu j as n goes to infinity for f in C of x, for any f in C of x. But we also know that this converges to Cf, to this constant that appears in the third condition. And this constant has no index j, right? It's just a constant that doesn't depend on the point, because that's what the third condition is saying. There's a limit, and the limit does not depend on the point. So the integral of f with respect to the first measure is equal to the integral of f with respect to the second measure. And that's true for all continuous functions. But by the uniqueness part in the Ries representation, this shows that the two measures agree. By the uniqueness in Ries representation, we obtain mu1 equals mu2, and that's what we wanted to prove. Four implies 3 is obvious. And 1 implies 3 is a nice exercise. 1 implies 4 is a nice exercise. I'll give you a hint. We used this claim from last week, right? In 1 implies 3, we used this claim from last week that whenever we look at this average 1 over n sum from j equals 0 to n minus 1, t, j star, any measure, this always converges to a t-invariant measure. And in 1 implies 3, we only needed the Dirac measure at x. And sort of one and the same Dirac measure we used all the time. But you don't have to. The claim is way more general. So you could choose different Dirac measures. And maybe if the uniform convergence doesn't happen, you could sort of choose for every n the point that gives you the reason why uniform convergence doesn't happen. And by doing that, you actually get a contradiction too. You will be able to construct a new invariant measure that is not mu that you started with. And then you get a contradiction. So that I'll leave as an exercise Not sure whether it can fit, but yeah. Good. So in the last 20 minutes, 25 minutes, I want to all right, what's a good example of a uniquely ergodic system? The circle rotation. We talked about that. And we can also go to higher dimensions if we take alpha 1, alpha 2, alpha n, and so on, alpha d, I think, and we have this condition that 1, comma alpha 1, comma alpha 2, up to comma alpha d are linearly independent over Q. We talked about this. Then the d-dimensional rotation system is actually ergodic, and it's actually also uniquely ergodic. And we proved this using, what was the condition? Condition-free. We proved this condition-free because we looked at the ergodic averages of an arbitrary point and showed that they converge to the integral with respect to the Lebesgue measure. And we proved this by proving it first for characters. And for characters, it's just a geometric series that you need to calculate. And because of the geometric series formula, you can find the limit, no problems. Then you can take the linear hull of characters, called trigonometric polynomials. And the same approximation statement that we made today can also tell you now that if the statement holds for all trig polynomials, the statement holds for all continuous functions. We have proven that step already today in the construction of the generic points. Okay, so that's one uniquely ergodic system. I want to give you a more interesting one, a more complicated one, and it has a nice number theoretic extension of the equidistribution of multiples of an irrational number, and it's kind of a theorem of Weyl that we can prove in the using the method more or less inspired by Fürstenberg. So for alpha irrational and f continues on the 0-1 interval, we have, when we average our continuous function, not at n alpha, that's the irrational rotation, but at n squared alpha, it converges to integral f dx with respect to the Lebesgue measure. No, that's not looking good. So it's j squared alpha, of course. So again, said differently, mod 1, the j squared alpha points equidistribute in the circle, which if you want to rephrase it as in a funky way, you can again talk about the Benford's law. So Benford's law holds not just for powers of 2, it holds for powers of 2 where the exponent is a square itself. So you could translate this to saying Benford holds for 2 to the n squared. And the alpha, the irrational number, is again log 2 over log 10, or log 2 of base 10. Never mind. Yeah, so how does this follow from a dynamical system? And this is a result of Fürstenberg, which rather quickly implies the result of Weyl. This is way more general. I mean, also the connection works more generally. You can look at other polynomials as long as one of the coefficients of the polynomial is irrational, you are happy. But the dynamical system that you need to build becomes more and more complicated, so I'm only showing you the first non-trivial instance of this connection. Right. Again, alpha is irrational. We define a dynamical system T on the two-dimensional torus, where I need to tell you what is happening to a vector x1, x2. And I do x1 plus 2 times x2 plus alpha in the first coordinate, and I do x2 plus alpha in the second coordinate. So in the second coordinate, I see the irrational rotation. In the first coordinate, I see something more complicated. I think I switched first and second in the discussion later. Never mind. Okay, so why does, we define that. What's the statement? Then T is uniquely ergodic with the two-dimensional Lebesgue measure being the only invariant probability measure on the two-dimensional torus. That's the statement, and maybe I first convince you why that theorem implies the statement of Weil. Proof of Weil using Fürstenberg. I just studied one single orbit, and then you will see the connection between the two. And if I want to study only one orbit, then let's take the most trivial orbit, 0, 0. So I want to know what happens with 0, 0. 0, 0 is mapped to alpha, alpha. Great. Alpha, alpha is mapped to, need to look at the formula. I get here 2 alpha. I need to add alpha once again to the alpha. And then I need to add to alpha. I need to add 2 alpha and then another alpha, also called 4 alpha. And then I apply my dynamical system again, and I get below 3 alpha. That's easy. And above, what do I see above? I get the 4 plus 4, which is 2 times 2, plus 1, also called 9. So simple induction will tell you that after n steps, you get n squared alpha in the first coordinate and n alpha in the second coordinate. That's why I put here the 2 here. That's kind of from the binomial theorem. So if you know that n squared alpha, n alpha equidistributes in the square, which is what unique ergodicity will tell you, then when you just forget the second coordinate, you get a sequence of points that equidistributes in the one-dimensional circle. So that's the end of the discussion why Fürstenberg gives you Weil. Because you get a stronger statement, you get an equidistribution in the product space. So, yeah. You could also try to translate this to a Benford's law statement if you want. It would be telling you something like the leading digit of 2 to the n has a certain distribution. The leading digit of 2 to the n squared has a certain distribution. But actually, these two distributions are independent. If you know the leading digit of 2 to the n, it tells you absolutely nothing about the leading digit of 2 to the n squared, which is what you expect, because how could it? But we can prove it. Okay. Okay, so how do we begin proving this unique ergodicity? Well, maybe an easy start would maybe to prove ergodicity. Because if we can't prove ergodicity, for this transformation with respect to the Lebesgue measure, how could we hope to prove unique ergodicity? So step one is the Lebesgue measure is ergodic. How do we prove this? Yes? The answer is always the same. I'm sorry. You're perfectly right, but you answered. So if you want to prove ergodicity, and the measure that you see here is a Lebesgue measure, just try Fourier series. So maybe that's another good exercise. I'll skip it today. Reason being, I have a committee on next Wednesday, and my colleague Manny Acker kindly agreed to jump in. So maybe I can get this almost done, and then he can start a new topic on next Thursday. Is ergodic. Proof uses Fourier series. Step two. What did I want to do next? The circle rotation is uniquely ergodic. That we already know. Known because of Fourier series. The trig polynomial discussion that I mentioned before. We did that a while ago. We didn't call it uniquely ergodic back then, but we really showed every point has an equidistributing orbit. Every point satisfies the ergodic theorem for every continuous function. Now I want to do, the argument I present is a little bit different than Fürstenberg does it, but it is the same idea in secret. I'll try not to confuse my two things. So I take a new measure, nu, which is the Lebesgue measure on the first coordinate, and a Dirac measure on the second coordinate. For an arbitrary x. And then I look at the ergodic average of this expression of this measure. I sum from j equals 0 to n minus 1, t j star nu. And I look a bit about what the transformation is doing and what is happening somehow with this measure when I apply the transformation. The first coordinate is kind of difficult, right? The first coordinate in my expression is this. This is where the quadratic stuff is happening, where the shear is happening. That's sort of the difficult part of the transformation. But if I put the Lebesgue measure on this first coordinate where the difficult part of the stuff is happening, I actually don't see these complications whatsoever. So the claim is that this is actually the same thing as the Lebesgue measure cross the average of the push forward measures under the one-dimensional circle. In the first coordinate, I have Lebesgue measure. Lebesgue measure is invariant under translation. Under any translation. Translation by alpha, translation by 2x2, it doesn't matter. The Lebesgue measure is invariant under translation. So by pushing Lebesgue cross the Dirac measure under this transformation, with respect to this transformation, the quadratic part, the first coordinate, is preserving the Lebesgue measure, and in the second coordinate, I just have the circle rotation. And this, because of step 2, converges to the two-dimensional Lebesgue measure. Okay. Yeah. If needed, we can come back to all of this on Friday, next week. Yes?
Even though it's already like
There's a star somewhere. Yeah. Thank you. Okay. So this converges to an invariant measure. Yeah, sure. It converges to the product Lebesgue measure on the two-dimensional torus. So the claim from last week is not particularly helpful yet. Now I do something slightly weird. I modify this. Let eta be positive and define nu eta to be 1 over eta, Lebesgue measure on the first direction. No, Lebesgue measure on the interval 0 up to eta, say, cross the Dirac measure. Yeah, I'm only interested in what happens at 0, but no, I'm interested at any point, x. Yeah. Yeah, I should have here an interval of length eta. So maybe this is x2, and then I have x1 and x1 plus eta. So it's a Lebesgue measure, but it's shorter than this Lebesgue measure here. Here I had the length 1 Lebesgue measure, and here I have length eta Lebesgue measure, but I normalize it to be a probability measure. Okay? Then, when I average this measure in using my usual expression, any weak star limit of 1 over n, sum j equals 0 to n minus 1, t j star, nu eta is t invariant, right? Agreed? That we understand. That was the claim from last week. It doesn't matter which measure we take. When we do this averaging, we always get an invariant measure. Now something else is happening. Namely, this is kind of a positive proportion of this measure here, right? It's sort of an eta piece of this measure. I can also look at the remainder of the Lebesgue measure that is not in there and define another measure, which is sort of the complement of this guy. We can repeat this. For torus without that interval, and obtain a second sequence with t invariant limits as well. Let's say mu eta tilde is a limit of this one. A limit, right, because we might need to choose a converging subsequence. And let's say mu eta tilde tilde is the limit for the other guy. Limit for the complement. Complementary measure right? Now, this was kind of a positive piece of that guy, and this is kind of the remainder of that guy. So what I'm hinting at is, before I take the limit, this is a convex combination of these two things. Namely, I just need to multiply nu eta with eta, and this measure, the second measure, with 1 minus eta, and sum it up, and then I get this guy, which I already understand. I'm aiming somewhere. Can someone see where I'm aiming? Moreover, if we use the same subsequence to make both converge, we have eta times mu eta tilde, which was the interval from x1 to x1 plus eta, plus 1 minus eta mu eta tilde tilde, is equal to lambda t squared, because that was the limit that we had when we had the full interval from step 3, because of step 3 and convexity calculation. Can now someone see what I could say now? If you, yes?
So mu eta to lambda of the complement times lambda.
No, they actually both converge to the same thing. Why do they both converge to the same thing? Yes?
Because we said the right-hand side is ergodic.
Yes.
So it as a convex combination.
Yes. Yes. Step 1 said this guy is ergodic, and we have written the ergodic measure as a convex combination of two invariant measures. So using step 1, we know that this is actually equal to lambda t2 because of step 1. And step 5, I only say it, is using uniform continuity to say that we are done. Because all you want to show is that for a given continuous function, the statement is true, and the statement that we got here is true for every eta. So if you now say, my f is continuous, I only care about an epsilon, and for this epsilon there exists an eta, then I'm in business, because this convergence happens for the given eta. It is a bit of a roller coaster, but in the end, one can actually prove the statement. And tell me if we should do it more slowly next Friday. Thank you.